Hello, class 11th physics chapter elasticity. Application of elasticity, and there are only three you can see, but there are lots many. I will include them also, but these are more some based upon some expressions and some calculations. That is why I have listed them out separately. So first thing, thickness of metallic ropes used in cranes. So I hope you people have seen such ropes, and they look like, if my drawing would help you, so they look like twisted wires. They look like this. This is called braiding, putting lots of wire together and twisting them over. So how can we decide that uh, how much thickly braided strand we require? So for that, first thing we should know is a factor of safety, which is equal to approximately 10 times, so which is considered to be as a safer limit, multiplied by load to be lifted. So let us suppose we have to lift a load of a car of, examply, if we take it, a car of 1000 kg, that is load equal to 1000 into 9.8, because load equal to mg, then so it will be 980 Newton. Well, next, so factor of safety equal to 10 times of load, so it will be 9800 Newton. So next thing, ultimate stress that it can bear. See, I am taking the case of an ordinary car, but anything can be asked in the exam, so you have to replace that load, and for factor of safety you have to multiply it with 10. Then ultimate strength of stress, actually ultimate stress can be called, so it is this load, this factor of safety, 10 into L upon area of cross sectional area of that rope. And all right, so next we know 10L upon pi r square. So if we want to find the radius, pi r square, okay, I will write all the steps upon ultimate stress, which we can say sigma. We represent stress with symbol sigma, and I'm putting subscript u for ultimate strength. And so r square will be equal to 10L upon pi sigma ultimate, and therefore r equal to root of 10 times load by pi sigma ultimate. And see, if we want to make rope of steel, then according to given condition, it will be 10 into 9800 upon pi, that is 3.14, times this ultimate stress for steel. It is for steel, okay, so it will also be given, so I'm taking it for steel. So for steel it is 3 into 10 to the power 8. So when we will solve this, once again I will use my approximate calculation, which is very very helpful. So it will be 3 3s are 9, little more than 9. So when we divide 10 by that quantity, which is a little bit greater than 9, so we will get something around 1.0 something. So I'm assuming it is 1.1, and so entire these can be reduced to 1.1. And when we multiply it with this 98 100. So now see a trick I'm doing. It is not exact calculation. You can use calculator or do some rigorous calculation here. I'm doing it directly. So this is my shortcut way to answer. This is entire this term is 1.1, and now I'm reducing that 1.1 to 1 and I'm raising it. So I'm making it. So I hope many students who have watched my earlier videos knows that this is how I do these approximate calculation, which has approximately 5% error. But okay, now to save time, that is most effective tool I have. So okay, it will be 10,000 now upon 10 to the power 8 is there. So 10 to the power minus 4, it will become 10 to the power minus 4. I don't think that anyone of you will have any trouble in this, and if you will have, then you can write a comment that this thing is not clear, so I can upload another video to show you entire calculation behind this. So all right, now it will come out from the root 10 to the power minus 2 meter. It is better to convert it into centimeters, so it is 1 centimeter. Still 1 centimeter is something like the size of my thumb, and this much thick strand we require to lift that that car. But it is difficult to make a rope using this much thick steel. It will look like a rod. So we take bit thicker, more thick than this radius. In fact, this is radius, so diameter will be this much. So it is very difficult to make the such a rope, such thick rope. So so to impart flexibility to the rope, um, it is made up of large number of thin wires braided together. So this is how we. That is why you often see in those uh, ropes made up of a large number of thin ropes, thin strands. All right. So this is how we'll go to measure thickness of required rope. Now next, designing of a beam for its use to support a load. This heading also includes another topic, bending of beam. So if we have a plank, then it will bend. It is supported on some knife edges. Then it will bend due to its own load, and it will get converted. Well, I have shown you, I have bent it heavily to show you the bending. Okay, now let us suppose its length is L, its breadth is B, and its thickness, uh, uh, length, breadth, depth. I'll use depth D for that. And okay, now it has depressed. This is the depression. It has gone down, and that depression is delta. So that depression in the bend, in the beam, depression, no, sorry, of beam, that sagging, you can understand that if you keep something like a paper. So instead, if I lift this, so it will sag at the midpoint. because its entire weight is acting at the center and it pulls it down. So depression of beam delta is equal to, here it sometimes become difficult, but Manglo cube, you have to put Manglo, we have memorized it like that. And before you die, and cube, you have to put cube here also. So Manglo before you die, and you have to remember these three. So what is this mg? It is the entire weight. L, that length. So greater the length, greater is the bending, and lesser is the depth, greater is the bending. Other terms are also there. Y is its Young modulus. So this is how this entire expression goes. Now, all right, this is a direct expression in your syllabus, so no need to worry about the derivation of this. So since delta depends on d cube of depth, so depression can be reduced uh, so by increasing depth, by increasing depth. There is a whole new problem if we use some kind of, so in order to support a bridge with the help of pillar. So according to this expression, with the greater depth of this pillar, the sagging here of this pillar will be minimum, but it could lead to another problem that is called buckling. So all right, this concept is that's all for this concept, but here we have to add this terminology also. So beam can ordinary beam can undergo buckling. To avoid this, I-shaped beam is used it look like this. This shape gives large load bearing surface. I am talking about this surface and this surface. Depth without buckling, with negligible buckling. And also reduces cost, because otherwise we require bit broader pillar there, and reduces cost. Estimation of height of mountain, well, this need to be corrected, can be sustained by the earth. Knowing this, we can calculate the possible height of mountain in any other planet, but knowing some other kind of facts of that planet. So for rocks, a mean density for rocks is nearly 3 into 10 to the power 3 kg per meter cube. It is not exact value, it is close about, but we are just estimating. So yeah, of course, we don't require exact sure shot calculation here. We need some estimation only. So if there is a mountain, then we will consider the height of that mountain, and if that is h, then pressure exerted at its surface, at its bottom, is given by h rho g. And we also have to find the ultimate strength of ultimate stress. So this is further equal to its elastic limit. So I'm not writing it separately, but it is its elastic limit of stress to be applied on it. Elastic limit of stress applied to it. We can also call it ultimate stress or ultimate strength of that material. So for rock, this limit, actually you don't require to memorize these values, but approximately I have this data. It is 3 into 10 to the power 8 Pascal. So now if we put the values here, so H equal to P by rho G. P is equal to this one. So 3 into 10 to the power 8 upon rho 3 into 10 to the power 3 G, approximately 9.8. I'm taking it 10. In the exam you can write here 9.8 and then approximate it to 10. So if we calculate it, it comes out to be approximately 10 to the power 4 meter. That is, yeah, I mean, it looks like this. And as per my general knowledge, height of Mount Everest is nearly 8,484. So if I'm wrong, write me in the comment, but this is what close to the height, that predicted height. Density might vary and acceleration due to gravity might vary, so it is not exactly 10,000 meters, but somewhat less than that, which is this. But these things are not exact. One thing for sure, that on earth mountain cannot be any mountain can never be of height greater than 10 kilometers. This is actually 10 kilometers, and this is what is there in actual practice. So, and if we talk about some other applications of elasticity, so here are some other uses. Machine part never subjected to stress beyond the elastic limit, otherwise they will become plastic, and they can break anytime. Bridges are declared unsafe after long use because they repeatedly goes on the cycle of deforming and regaining themselves. So after longer use, it start reaching permanent set region, and then it turns to be having plastic nature. Before construction of building, soil test is done to test strength of soil against stress of load of building. So we test that soil, or we fill some foundation, and so soil test, after soil test, it is confirmed that how much floors and what material could be beneficial for that building. And there is to identify and or select more ductile material, etc., as per requirement. So we know that the stress strain graph, on the basis of that we can categorize material and select accordingly. So that's all in this video. I hope this topic, this chapter is clear to you, and there are more videos on elasticity. Check those videos also. That's it. Bye bye.